Okay, so 18.1 notes is going over the definition of an nth root. So we're going to talk about the concepts of definition of a square root, definition of an nth root, roots of variable expressions, the Pythagorean theorem, and radical functions. Okay, so we are stepping away from quadratics and now into radical. Okay. So for the first concept, it says definition of a square root. So we know that b is the square root of a if b squared equals a. So what this is saying is that if we were to take the square root of that b squared, then we would get our a value. Okay. So what we're doing in these problems is we are identifying square roots of real numbers. So we are just taking the square root of all of these examples here. And we know that the square root of a perfect square root is going to be the same two numbers. So for example, 25 is the same as saying 5 times 5. So that means the square root of 25 is 5. That's all we're doing in this problem. Okay. 49 is the same as what two numbers multiplied together? 7 times 7. So that means the square root of 49 is 7. So notice how it's two multiples of the same number, 7 times 7. What about 0? Remember, we're doing the multiplication part first. So 0 is the same as saying 0 times 0. And so the square root of 0 is 0. Okay, let me see if I talk about...
So as far as our course is
Yes.
concerned, involving 0 is the only time it's undefined is when it's in the denominator, pretty much?
Correct.
Okay.
And that's going to be all cases.
Gotcha.
Yeah. Okay. And then now we have -9. Are there two numbers, if we multiply them together, the same number would give us a -9?
No.
No, because we could do 3 times 3, and that's +9. Or we could do -3 times -3, which is also +9. We would never get a -9. So that means if I take the square root of -9, that should give us what?
Is this one of those things where you can factor out the -1?
More advanced courses.
Okay.
Just think of it. Can we take the square root of a negative number?
No.
No, so it would be no solution. No solution. No solution. I don't think in this course we even talk about imaginary numbers or anything. So it's just no solution. Okay? So again, that's just an introduction to what we're kind of doing. So this is the simple part. Okay, we can have positive or negative square roots. So we saw that above. We saw that if we have the square root of a positive value, then we're going to get a positive square root. So when we took the square root of 49, we got 7, both positive numbers. Okay. We could have a negative outside of the square root. That is okay. If it's outside of the square root, then we would just take the square root of whatever that value is and attach a negative to it. Okay. And then here, just to note, like we saw above, if we take the square root of 0, we get 0. Okay, so we're going to do the same thing here. So now it's giving us all these square roots, and we're going to have to simplify. So what's the square root of 36?
6.
Good, it's 6. because 6 times 6 is the same as 6 squared, which is 36. So since we're taking the square root, we had two of the same numbers, so 6 and 6. What do we do when we take the square root of a fraction?
The square root of the numerator and the denominator.
The top and bottom. So if you remember from the properties of radicals, a long time ago, we can take the square root of a fraction by separating the numerator and the denominator. So we could write this as the square root of 4 over the square root of 9, and that's the same thing. So then we simplify them separately. What's the square root of 4? 2, and then the square root of 9? 3. So that means the square root of 4/9 is 2/3. Which means if we do 2/3 times 2/3, we're going to get 4/9. Two multiples of the same number. Okay. Same thing with decimals here. So we have the square root of 0.04. Looking at just the 4 here, can we take the square root of 4? Yes, we can. So that means we can take the square root of 0.04. And if you type it into your calculator, you're going to get 0.2. So this is something you would just type into your calculator. And you're going to get 0.2. Because if we took 0.2 times 0.2, that would give us 0.04. What's the difference between D and E?
D. Oh yeah, but for the negative is that the negative's on the outside of the square root.
Yeah, so for D and E, we have the negatives, one on the inside and one on the outside. Which one is going to be no solution, D or E?
D.
D, no solution, because we cannot take the square root of a negative number. So that negative can't be inside. Okay, what about E? Good, we would just look at this square root of 144, which we know is 12, and then we have to bring the negative with it. So this one is going to be negative 12. Okay. So that one we just took the negative and brought it with our answer. What about F? What's the answer for F?
No solution.
No solution. Why?
Negative sign.
Good. This is no solution because we can't take the square root of a negative number. No solution. Would part G be no solution?
No.
No. Why?
Negative's on the outside.
Because the negative's on the outside. So since we have the square root of a fraction, how can I rewrite this? Good. Square root of 1 over the square root of 9, and I'm just going to bring that negative with us. So what's the square root of 1? And what's the square root of 9? 3, and then again, I just bring the negative with us. That means our answer is negative 1/3. So the only way you would have a negative in your answer is if the negative was outside of the radical, the square root. Any questions on concept 1 of taking the square root? Okay. concept 2 talks about the definition of the nth root. Okay. So we say b is the nth root of a if b to the power of n is equal to a. All this is saying is that we can have more than just the square root. We could have the cube root. We could have the fourth root, the fifth root. The only difference here is that instead of having two of the same numbers that can multiply into that radical number, we would have multiple. So for example, if you look at, let's see, the third example here, it says the fourth root of 16, 2 is the fourth root of 16, because if we do 2 to the fourth power, we get 16. Same with evaluating the nth root of a number. So this is just describing the nth root, this is evaluating the nth root. So in the example here, let's zoom in right here. In this example, we have the fourth root of 625, meaning we're looking for the same number. If we multiply it by itself 4 times, gives us that 625. In this case, that's 5. This is something you should be able to do on your calculator. Okay, you should be able to, if you have the simple scientific calculator that's required for the course, you will be able to type in the fourth root of a number and get an answer, the fifth root of a number. Okay. The only difference here between this one and the square root is that if we have a root of a negative number, it's not always no solution. So we see that example here. So if that nth root is odd, so odd numbers, 3, 5, 7, so on and so forth, and we have a root of a negative number, then our answer is going to be negative. Because if we had, for example, this problem here, we could take -2 times -2 times -2, so that's the third root 3 times, multiply them together, and we would get -8, which is under that radical. So our answer can be negative if the nth root here is odd. We'll see that in the examples. Okay, so let's look. What I have here is just a chart for you to use. Again, all of this can be found using your calculator, but I just decided to add this to the notes just so you had it. Okay, so this is just a chart for you to use. Another way to look at this chart is this number could be inside of a radical. So this could be the fourth root of 81, and the answer is 3. So we can look at it in either direction. So 3 to the fourth equals 81 is the same as saying the fourth root of 81 is equal to 3. Same with this one down here. We can look at this 625 and this fourth root. So this is fourth root of 625 is equal to 5. Okay. So this is a good chart to have available to you when we are taking the exam. Okay, so I would star this in your notes. Okay. So let's look at some examples. Okay, so it says simplify if possible, meaning it's not always going to be possible, right? Because sometimes we're going to get no solution. So looking at A, this is just a normal square root. What's the square root of 4? 2. This one was just a normal square root. Okay. This one wants us to find the cube root of 64. So again, you could do this two ways. You could type this into your calculator, cube root of 64, or we could solve this by hand using the prime factor tree. Okay, remember we did this a few notes back. So remember when we're doing the prime factor tree, I'm going to take that number of 64 and I'm going to start dividing it by prime numbers. So my first prime number is 2. So 64 divided by 2 is 32. Circle that 2 because it's prime. And then 2 can go into 32 how many times? 16. 2 can go into 16 how many times? 8. So we're trying to end at a prime number. 2 can go into 8 how many times? 4. And then 4, 2 goes into 4 how many times? 2 times. So once we end with a prime number, we're going to look at all those prime numbers we circled, and we are going to pay attention to what our root is. So our root is that number outside of the radical. So what number is that? 3. So I'm going to circle pairs of 3s. So I have this pair, right? Because those prime numbers of 2, 2, and 2. And then I have this pair, these prime numbers of 2, 2, and 2. Once I have my pairs, I'm going to take one number from each of them. So that means I'm going to take a 2 times another 2. 2 from my first pair, 2 from my second pair. Multiply them together and I get 4. That's my answer. So the cube root of 64 is 4. So again, you could choose to use your calculator, or you do this by hand, which is the prime factor tree.
Can you repeat that part about what to do after circling the pairs of 3s? You circle the pairs of 3s because you have a cube root.
Yes.
But then how did you decide to multiply the 2s?
Because I took one number out of those pairs. Yes.
Oh, okay, gotcha.
So since I had a pair of 2s, I took a 2 out. Then I have another pair that's 2s, I took a 2 out. If these ones were 3s, then this number would be a 3.
Gotcha.
So it's whatever that number is that I'm circling in the pairs, I take 1 out. Okay. Okay, so let's do the same thing for letter C. I'm going to ignore that negative for now. That's inside the radical. And I'm just going to do my prime factor tree off of 32. So 2 goes into 32 16 times. 2 goes into 16 8 times. 2 goes into 2 goes into 8 4 times. And then 2 goes into 4 2 times. So I ended at a prime number 2. How many am I going to be circling in my pairs? 5, because that's the number outside of the radical, that 5. So when I circle my pairs of 5, how many pairs do I have? 1. So that means the only number I'm pulling out is what? 2. Okay. However, we can't say that the answer is just 2. Because if we did 2 times 2 times 2 5 times, would we get a negative 32? So that means our answer has to be a negative. So it's going to be a negative 2. Okay, we know that for 2 reasons. We have a negative inside of the radical, and our nth root is odd. So we have a negative inside the radical, and that nth root of 5 is odd. What if that nth root was even? What would our answer be?
Solution.
No solution. So if this nth root was even, so if it was a 4, a 6, an 8, so on and so forth, there would be no way we could have a negative inside of the radical, so it would be no solution.
But without the negative, there is a solution.
Correct. Correct. Okay. Okay, for this one, we have 81. So we're going to do the tree for 81. So we start off and we say, okay, can 2 go into 81? No, because that's our first prime number. We always check 2. 2 can't go in, but 3 can. 3 goes in 27 times. 3 goes into that 9 times. And then 3 goes into 9 3 times. Okay. How many numbers is going to be in our pair? 4, because of that nth root. So I'm going to circle my one pair of those 4 3s. And so my answer is going to be what? 3. For part E, we have the 6th root of 1 million. Okay, I'm not going to do the prime tree on this. That's going to take forever. So another way that we could write 1 million is we could write this as 10 times what? Yeah, we could do 10 times 10,000, or it would be like 10 times 10 times 10 times 10. 1, 2, 3, 4, 5 times 10. 6 times. Because when we multiply 10, the number of times is going to give us the number of zeros in that problem. So this is 1 million, meaning we would have to multiply 10 6 times because there's 6 zeros here, right here. Okay. So knowing that, what is our pair that we're going to circle? A pair of 6. And so since there were 6 tens, our answer is going to be
6. It's going to be
10. Remember, we take one number out of our pair, and since we had a pair of tens, our answer is 10. This would only be the case if you are talking about like 100, 1,000, 10,000, 1 million. It has to be one that it has all those zeros at the end. Or you could type that into your calculator.
What if it was something different?
Like 1,562, something like all those numbers. Calculator. I mean, or you could do the prime tree, but that's going to take you pages and pages and pages of work. Just use your calculator. Yeah.
But I'm typing it in and it just gives me like a decimal.
Gives you a decimal.
Yeah.
Are you using the 6th root or the square root?
Yeah, 6 root.
The 6th root?
I mean, unless my
Yeah.
calculator is not set up right. But earlier I did one of them, I guess it was 130 or 300 and something.
Mm-hmm.
And it gave me 5, so.
Yeah, just double check that it's the 6th root. Try putting the 1 million in parentheses and see if that changes anything. But it should give you 10. Okay, F, square root of negative 100. What's the answer here?
No solution.
No solution. Why is it no solution?
Negative.
There's a negative inside that radical, and our nth root is positive, because if we don't see an nth root here, we assume that this is what? the square root, and what's the number for square root? 2. Okay. So if our nth root is positive and we have a negative under the square root, it's no solution. So knowing that information, what's the answer for G? No solution. Because our nth root is what number? 4, and 4 is positive or negative? Or not even or odd. That's what I meant to say. Even or odd. It's even. Okay. Okay. Next concept here says if n is a positive odd integer, so an odd number, and it's talking about this right here, this nth root right here, if it's odd and it has the matching exponent that is also odd, these will cancel and you're left with the number inside. So this is saying that if you take the square root of 4 and then square it, what's going to happen to those square roots in that square? Cancel, because they're opposites of each other. So that means the answer would be 4. Okay, so if they are the same and they are odd, then the answer is just whatever is inside of that radical. If our nth root is even, so even right here, it's still going to be whatever is inside of that radical, but it's going to be the absolute value of that. That means that the only answer we can plug into this problem has to be positive. That's why we do the absolute value. So actually this would be the absolute value of 4 because our integer, our nth root integer is even. Okay. So let's look at some examples here. So first, looking at our nth root. Even or odd? Even. So since it's even, our answer is going to include the absolute value bars. Okay. Is this nth root match the exponent? Yep. Since they match, that means it cancels. And we're left with just whatever is inside the radical. And what was inside the radical? But we have to put absolute value bars around it. And those absolute value bars do what to our problem? Yep, makes it positive. So our answer is 3. And that is only because our nth root was even. Okay. What about part B? Is that nth root even or odd? It's odd. So are we going to have the absolute value bars? No. Does our problem here have the same nth root as the exponent? So it cancels and we're left with what as our answer? -3. This time we leave it as -3 because our nth root was odd. So we're just checking even versus odd. Okay. If we don't see an nth root, then we assume what number is here? A 2. Is that 2 even or odd? Even. So what does even tell us? Absolute value bars. Are my nth root and exponent the same?
Yes.
So they cancel. So that means my answer is going to be what?
X plus 2.
Absolute value of x plus 2. And I can't simplify that further because of the variable. Okay? So this would remain absolute value of x plus 2. Okay. Now, letter D, that it's supposed to be a 3, not a 6. Okay, because right now we're working with the ones that match. Okay, so looking at that nth root, even or odd? What does that tell us?
No absolute value.
No absolute value. And does my nth root match my exponent?
Yep.
So they cancel. So that means my answer is
Must be.
A plus B.
Wait, so how'd you turn the 6 into a 3?
No, that was a mistake. Typo. It's supposed to be a 3. Yep, typo. It's not me randomly changing it.
Does Marcos, can you explain why it's not absolute value?
So the only way it's absolute value is if that number, that 3, was even. So like on part C, since 2 is even, we have the absolute value. 3 is odd, so we don't have the absolute value. Okay. So for part E, notice we now have 2 different values because what value is here if we don't see anything? A 2. Is that 2 even or odd? Even. So that tells us what? Absolute value bars. So it wants us to take the square root of y to the 4th. So ignore the y for now and think of this as the square root of 4. What would our answer be? 2. But we have the y there, so technically our answer is going to be y squared with the absolute value bars. Good. Okay. So if we had other cases where the numbers were different like that, if we could not take the nth root of that number, so for example, we took the nth root, so the square root of 4, if that was not possible, then that means it can't be simplified further, okay? So not no solution, we would just say can't be simplified. Because there's an answer there, it's just already simplified.
So if the 4 would have been a 3, it'd just be like a 6 instead of a 4. It'd just be y.
So if this 4 was a what?
A 6.
A 6? Well, then you would ignore the y, and can you take the square root of 6?
Yes. 3. Oh, no.
No. If it was a 9,
Okay.
then you would take the square root of 9, and that would give you 3. But we'll talk about these type of problems a lot more in the upcoming notes. Okay. Okay, again here, this is just a diagram with information for you to have. So
The same one like earlier or different?
this one's different because it has the variables in it. So this one is talking more about the properties of exponents. So right here, the properties of exponents. This property of exponents tells us that if we have a exponent raised to another exponent, we multiply the exponents together. So for example, x cubed squared means we take this 3 and 2 and we multiply them and we get x to the 6. Okay? Or if we have x cubed cubed, it's a power raised to another power, so we multiply them and get 9. Okay? Again, this is just a chart for you to refer back to for the exam. Okay. So for this next part, we're going to be simplifying these expressions by using the knowledge of the perfect squares and perfect cubes. So looking at part A. Okay. Part A. Seeing how I describe it here. We know that y to the 8th power can be rewritten as what? Yes, y to the 4th squared. So like up here, how we had this part here, x to the 4th squared is the same thing as x to the 8th. So we could say that y to the 8th is the same thing as y to the 4th squared. Okay, so we're referring back to that chart. So this is the same as saying y to the 4th squared. The reason we're rewriting this is because we want to ultimately cancel that radical with the exponent. So since we don't see a number here, what number is there for the nth root? 2. 2 is even or odd? Even, so are we going to have the absolute value? Yes. And then does the nth root cancel with the exponent?
One of them,
Yep. So we're only looking at that part here. Those 2 cancels. It's even, so we are going to have the absolute value of y to the 4th. Yep. So here we're just rewriting the expressions as perfect squares or perfect cubes, so we're able to cancel out that radical. Okay, and if you haven't caught on yet, this part's the radical. The reason I can't always call it the square root is because our nth root changes every time. So this is the radical. Okay. Looking at part B, notice that we have a number and we have a variable. So this could be rewritten as the cube root of 27 times the cube root of a cubed. Okay. So I separated my numbers and I separated my variables just like I did when I had a fraction, how I separated it for the numerator and then the denominator. Okay. I can only do that because the 27 and the a cubed are being multiplied. So we can first do the prime factor tree for 27 to solve. So we're looking at our prime numbers and we always start with the prime number 2. Can 2 go into 27? Okay, so we check our next prime number 3. Can 3 go into 27?
Yes.
Okay, 9 times, and then 3 goes into 9 3 times. Okay, that means we are going to be looking for pairs of 3 because of this radical. So that means the answer for that first part is going to be what? 3. So equals 3 so far. What about that next part? We have the nth root, the third root of a cubed. We don't have to because they cancel. Good, because they match. 3 and 3. So if they match, they cancel and we're just left with a. Does any of this need to be in absolute value bars?
No.
No, why not?
Because the exponents are odd.
Good, because the nth root is odd. So 3a. Okay. How could we rewrite C? Good, so
To fifth.
yes, we would give that fifth root to each part. Okay. Our fifth root is odd, so are we going to have absolute value? Okay. No, we're not going to have absolute value. And what happens right away to each of these fifth roots since the variables are being raised to the fifth power? Cancels. So that means we are left with what? A over B. Okay, here we're going to do the same thing, but notice not only do we have a fraction, that numerator, we can divide and split that up into how many parts? 3 parts, because we have the 81, the x to the 4th, and the y to the 8th. Okay, so let's go ahead and split that all up. We have the 4th root of 81, the 4th root of x to the 4th, the 4th root of y to the 8th, all over the 4th root of 16, and we're just bringing that negative out to the front. Okay. So starting with the 4th root of 81, I'm going to rewrite it down here. I'm going to do my prime factor tree. And what's the first prime number that can go in? 3. And 3 goes in how many times? 27. And then 3 goes into 27 9 times. 3 goes into 9 3 times. So that means we're going to have pairs of 4, which is just that one pair here, meaning that first answer is going to be 3. So equals, and I'm just bringing that negative into part of my answer, so I'm going to write negative 3. Okay, does that 3 need to be in absolute value bars? Yes, because the 4th root is even. Okay, so putting that 3 in absolute value bars. Remember that negative came from outside of the entire problem. That's why it's not in those absolute value bars. That negative came from here. I'm just placing it on the outside so I don't forget it. Okay. Now let's look at the next part. We have the 4th root of x to the 4th. What's going to be the answer here? X. And is that x going to be in absolute value bars? Yes, so absolute value, x. Okay. How could we rewrite y to the 8th so we would be able to cancel out that 4th root?
Y to the 4th times 2.
Y squared?
Yes, y, so good. We're going to have this rewritten as the 4th root of y squared to the 4th power. When we do that, we can cancel out the 4th root, and we're left with y squared. Is that y squared going to be in absolute value bars? Yes. Okay. Now the last thing we have to deal with is that 16. So I'm going to rewrite at the bottom so we can do our prime factor tree. Okay, what's the first prime number that can go into 16? 2, and then we're left with 8, and then 2 again. We have 4, 2 again, we're left with 2. How many pairs am I circling? 4, meaning my answer for this is 2. Okay. So to simplify this even further, notice how I have the absolute value of 3, absolute value of x, and the absolute value of y squared. Can I put them all inside one absolute value? Yes, because we're being multiplied here. So that means this is equal to negative absolute value of 3xy squared all over 2. Well, absolute value of 2, right? Because of that. Because of the 4th root of 16 is even.
So just to be sure, because of that, you could still put the entire fraction in this same exact absolute value.
Correct. So you could write this as negative absolute value of 3xy squared over 2 absolute value.
Gotcha.
Okay. Any questions on that concept? Next concept is the Pythagorean theorem. So this is just a review of middle school, high school math. Okay. Who remembers the formula for a Pythagorean theorem?
A squared times B squared equals C squared.
Perfect. A squared plus B squared equals C squared. Okay? If this triangle was not labeled, what do we know for sure that the C value has to be every time? Good, the hypotenuse. And I don't remember how to spell it. Hypotenuse, or just the slanted line, right? That's the hypotenuse. Okay. But in this case, it labeled it for us. So we have A is 5, B we don't know, and C is 13. So we're going to plug this into our formula. So A squared plus B squared equals C squared. A squared is 5 squared. B squared we don't know. C squared is 13 squared. Okay, so simplifying this, what's 5 squared? 25 plus B squared equals, what's 13 squared? 169. What are we going to do to solve for B?
Subtract 25.
Good, subtract 25. And we get B squared is equal to
144.
144. Okay. How do we solve for B? Good, square root. Why do we take the square root?
To cancel out the square.
Good, because remember that square root has that 2 there, and those cancel. So that means we are left with B is equal to square root of 144, which is 12. Okay. So the reason why we look at the Pythagorean theorem is because we are using this skill here that we just learned. That if we have the same nth root with the same exponent, they cancel. Okay, let's look at number 7. Number 7 says 2 boats leave the dock at noon. One travels due north at 6 miles per hour. The other travels due east at 8 miles per hour. How far apart are the 2 boats after 2 hours? Okay. So here, they already set up the diagram for us, okay? They set up what A and B is, and we are missing C. So again, we're going to use the quadratic formula and plug everything in. So I have A squared, so 12 squared, plus B squared, so 16 squared is equal to C squared. What is 12 squared? 144. What's 16 squared? 256 equals C squared. What do we get when we add 144 and 256? 400 equals C squared. How are we going to solve for C? square root, because that cancels out that square. And what's the square root of 400? 20. Okay. This is just answering the, good, yes, the miles. So if we were to write this in a sentence, we would say the boats are how many miles apart? 20 miles apart. So boats are 20 miles apart. Okay. Now let's look at the last concept here. Radical functions. Okay. So far what we've been doing is we've been simplifying radical expressions. Remember, the difference between an expression and an equation is if it has that equal sign. So in this case, we are dealing with function f of x is equal to the nth root of x. This is standard form for radical functions. It says if n is even, so if our nth root is even, the domain is restricted. If n is odd, then the domain is all real numbers. So in these questions, we are just finding the domain of each function. Okay? So looking at part A, it says g of t is equal to the fourth root of t minus 2. That fourth root is what? Even or odd? Good, it's even. Since it's even, that means the domain is restricted. So what that means is that if we have the square root of something, we know that that square root also has to be even. Okay? So, yes, even, positive. So we're going to take whatever is inside the square root, so t minus 2, and we are going to set that equal to greater than or equal to 0. Because it has to be a value that is positive. Because we cannot take the square root of a negative number if our radical is even. So that's why it has to be a positive number. So greater than or equal to 0. So then we just solve for t. So what are we going to do with that negative 2? Yep, add. Does that change the inequality? Nope, so we have t is greater than or equal to 2. That's our answer. Because here we're just finding the domain. Okay? Looking at B, is our function nth root even or odd? It's odd. And what do we know about an odd nth root? The domain is all real numbers. So we don't got to do any math here. It's just all real numbers. Because it doesn't matter if our radical gives us a positive number or a negative number because of that odd nth root.
Can we still do that Rolls Royce sign?
Oh, yes. You could do that. Yep. Okay. Part C, is our nth root positive, or sorry, even or odd? Even, because we don't see a nth root there, so we assume it's 2. So since this is even, what are we going to have to do to the part under the radical? Good, we're going to set it equal to greater than or equal to 0 because it has to be a positive value. So that means here we're solving for x. So what are we going to do first? minus 3. So we got to get rid of that minus 3 first before we mess with the 5 in front of the x. Does that change the radical? Or sorry, the inequality?
No.
No. Now what do we need to do to get x by itself? Divide by -5. Does that change the inequality?
Yes.
Yes, so it's going to flip in the opposite direction, and we get x is less than or equal to 3/5. So that means the only numbers that would work for x would be any number that is less than or equal to 3/5. So that those numbers would be 0 or anything negative.